Hey everyone, this is 12.3 Permutations and Combinations. I want to bring your attention back to example 6 on page 618. This is where we had um, this psychology class. We had 10 students, we had 6 chairs in the front row, and Louise had to sit next to her tutor. We had to figure out how many ways we could do that. In that problem, the way we did is we started by picking a spot for Louise and her tutor, and then figuring out how many slots or how many ways we could arrange the rest of the students in those seats. So, like for this example, if you put Louise and the tutor right in front in the first 2 seats, you have 4 seats left, and there's 8 students left to place. So you can put any of the 8 students in this seat, any of the remaining 7 students in the next one, the remaining 6, and the remaining 5. And this part of the question, how many ways can you arrange 8 students in 4 seats, is what we call a permutation. There's no repetition because the same student can't sit in multiple seats, but the order does matter. And in this section, the idea of order mattering is going to make a big difference. It's going to basically determine whether you use a permutation or combination. And the way I recommend you figure out if order matters or not is by picking a combination and then switching the order and asking yourself, is it a different outcome? So let me just show you real quick how that would work. Let's take these 4 seats over here to the right, and let's say I have student A, B, C, and D. Okay, so just generic letters representing different students. So those are 4 students that I picked, and I arranged them in those seats. So if I want to check to see if order matters, I'm going to stick with the same letters, A, B, C, and D, but I'm going to switch up their order. So maybe like a D, B, C, and A. Right, so notice the same 4 students got sat in those 4 seats, but I changed the order. And the question is this a different outcome in this situation? Well, in this case, this is a different outcome because if you're making like a seating chart, for example, the order in which they sit are going to correspond to them literally sitting in different seats. So in this specific case, when we're talking about sitting students in seats, order matters, and that means we're going to use a permutation. So again, I'm just trying to illustrate to you how you can determine whether order matters or not, because you're going to be asking yourself that question a lot in the coming problems. So let's dive into this permutation combination stuff. So we're going to start with permutations, and a permutation is selecting objects from a set and arranging them in a straight line. So again, just like in the last example, you're selecting objects or students from a set of 8, and you're arranging them in a straight line of 4 chairs. And in that case, we call it a permutation, and we say that the order definitely matters, which is what I put up here in red. This is the formula for permutation, by the way. It starts with a P for permutation, and you have an N and an R. N is the number of objects to choose from. So again, in our last example, that would be 8, because we had 8 students that we're trying to arrange. And R is the number of slots that you're trying to put them in. R would be 4 in that last example, because you had 4 seats. And the formula for that is N factorial. That's how we read this exclamation point. This might be new notation to you, which is okay. I'm going to explain that in just a second. But it's called a factorial. So this is read N factorial divided by N minus R factorial. So that's how the formula works. And let's quickly, I'll tell you how factorials work. So if you have something like 4 factorial, which again, that's how you read this statement here, 4 factorial. 4 factorial means you multiply 4 times 3 times 2 all the way down to 1. So 4, 3, 2, 1, multiply it all together, you get 24. So that's what 4 factorial equals. Just equals 24. It equals 4 times 3 times 2 times 1. Similarly, 6 factorial would obviously be 6 times 5 times 4 times 3 times 2 times 1. So you just multiply in descending order all the way down to 1. So in this case, 6 factorial would be 720. So I think that makes pretty good sense. The only thing that's kind of weird here is that 0 factorial, we're actually going to call that 1. So it's not 0, which you might think, it's actually 1. And this is for a variety of deeper mathematical reasons that I'm sure you're not interested in, but this will show up every now and then. In fact, I'll show you an example in a second where if you're following this formula, you'll get a 0 factorial. And it's important that you call it 1 because if you call it 0, often you'll have a 0 in the denominator, and that'll be undefined. So keep in mind we are defining 0 factorial to be 1. Alright, so let me show you how you can compute a factorial here. So we have a permutation of 8 and 4. So 8 is N and 4 is R. So in the formula, it's going to be N factorial on top, which is in this case 8 factorial, divided by N minus R factorial. So that's 8 minus 4 factorial, just like that. Let me change the size real quick. Okay. And 8 factorial we know is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all divided by, well, 8 minus 4 is 4. So this is just 4 factorial on the bottom, which is 4 times 3 times 2 times 1. Alright, so I'm just expanding this out. On the top, 8 factorial is 8 all the way down to 1 multiplied together. Here, 8 minus 4 is 4, so we get 4 factorial on the bottom, which is 4 times 3 times 2 times 1. And if you notice, I have the same 4 times 3 times 2 times 1 on the top. So I can actually cancel this piece with this piece, right? Because they're the same numbers and they divide out to give you 1. So really what we're left with is just 8 times 7 times 6 times 5. And if you multiply that all out, you should get, strangely I don't have it written out, but I'll give it to you. 8 times 7 times 6 times 5. You should get 1680, 1680. Alright, so that's a comma there, by the way. I'm just trying to illustrate to you how you compute a permutation and how you use these formulas with factorials. So that's P of 8, 4, a permutation of 8 and 4. One more example, P of 3, 3, we're doing a permutation again. So N is 3 and R is 3. So we get 3 factorial over 3 minus 3 N minus R factorial. This is 3 factorial over 0 factorial, right? Because 3 minus 3 is 0. So I want to remind you that 3 factorial is 3 times 2 times 1. 0 factorial is just actually 1. It's not 0. So this is just going to give you 3 times 2 times 1, which is 6 over 1. 6 over 1 is still 6. So that is a permutation of 3 and 3. So I just wanted to give you another example where you see that 0 factorial. Don't freak out. 0 factorial in this case is going to be 1. Okay, so that's a permutation. A combination is very similar. It's how many ways to choose R items out of a total of N items. In this case, order is not going to matter. You're not arranging things this time. You're literally just selecting a number of items out of a larger set. So here, over here, our notation is going to be a C for combination, still N and R. N is the number of items to choose from, so the total number of things you have. R is the number of items that you're choosing. So very similar roles here. The formula is actually very similar as well. The only difference is this R factorial in the bottom. So still N factorial, this time divided by R factorial times N minus R factorial. And again, we'll deal with all the factorials just like we did before. Alright, so I want to tie this into an actual problem here so you kind of get some context. On page 632, number 34 says we're selecting roommates. Annette has rented a summer house for next semester, and she wants to select 4 roommates from a group of 6 friends. Now your job in a problem like this is to determine whether it's a combination or a permutation. And the way you determine that is whether order matters or it doesn't. So here she has a group of 6 friends and she wants to select 4 roommates. And you have to ask yourself, does the order in which she selects these roommates matter? Well, she's not saying anything about the 4 that she's selecting. She's not saying she's going to select 4 roommates and one's going to room with her and the other ones are going to have their own rooms or anything like that. As far as we know, these 4 roommates are all in equal standing. So the order that she selects them does not matter. And that's the first thing you have to note. Order doesn't matter. She's just simply choosing 4 out of 6. So that automatically means we're going to do a combination. So we're going to have a C. And now we have to determine our N and our R. N is representing the number of objects to choose from, and R is representing the number of objects to choose. So we're choosing from 6, right, because you have 6 friends to choose from, and we have to select 4 of them. And that's what that stands for. That's what C of 6, 4 means. It's selecting 4, the number of ways you can select 4 out of 6. And obviously, if we calculate this real quick, I'll show you. We'll have N factorial on top, so 6 factorial. There's an R factorial down here, and then an N minus R, which is 6 minus 4. So this simplifies to 6 factorial over 4 factorial, and the 6 minus 4 is obviously 2, so we get an extra 2 factorial. And if we expand this, we're going to have 6 times 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 times 2 times 1. So let me show you all these pieces here. On the top, this is your 6 factorial. This 4, 3, 2, 1 is your 4 factorial like you had over here. And this 2 times 1 is your 2 factorial. Right, so all your pieces are there. We'll cancel what we can. Looks like we cancel the 4, 3, 2, 1. Oops. The 4, 3, 2, 1. Come on. With the 4, 3, 2, 1. Okay. And so what we're really left with is just 6 times 5 on top, which is 30, over 2 times 1, which is 2, and that gives us 15. Right, so the answer to this question, she's trying to select 4 roommates out of a group of 6. She has 15 different selections she can make, 15 different sets of roommates that she can actually choose in this case. And again, the first thing you always want to start with is figuring out if order matters or not. If order did matter in this case, we would be doing a permutation instead of a combination, and we get a different number at the end. So order doesn't matter in this case because she's just selecting the 4. She's not assigning them to specific cases. If you rearrange the order of the 4, you still have the same 4 roommates. Alright, so same page, 632. These problems, by the way, aren't asking us to actually get the number. They just want us to set it up. So is it a permutation or combination, and what is your n and your r? So I'm just going to set it up, and then we're actually going to do these calculations on the calculator, which I'll show you how to do afterwards. But let's see if we can go through each of these 4 examples, figure out if it's combination or permutation, and what our numbers are. So page 632, number 35, this is a baseball lineup. Joe has already chosen the 1st, 2nd, 4th, and 9th batters in the batting lineup. He has selected 5 others to play and wants to write their names in the batting lineup. So 1st, 2nd, he needs to choose the 3rd. He's already chosen the 4th, so he needs to choose the 5th, 6th, 7th, and 8th. That is 5 slots, by the way, 5 places he needs to place them, and he has 5 players to fill the slots. So our n and r are definitely going to be 5 and 5 because there's 5 slots to fill. If you go through 1st to 9th and pick out the ones he's already done, there's 5 slots that are open, and he's selected 5 others to play. So n and r are 5. The question is, does order matter or does it not? So it's pretty clear. They're talking about orders, right? 1st, 2nd, 4th, and 9th. The order is definitely going to matter here because the five people that he chose are definitely going to be in the batting lineup. The only thing that's going to be different is literally the order in which you put them in. So since order matters, that means we're going to choose a permutation. And we already said n and r are 5, so we get p of 5, 5. That'll tell you all the ways you can select the 5 people and switch their orders around. Okay, so the first one is permutation 5 and 5. Number 36, there are 7 boats that will finish the America's Cup yacht race. Alright, so there's 7 boats. They could come in any place from 1st to 7th place, right? And the question is, does order matter here? Well, I think so, because literally the only thing that matters is what order they finish in, right? 1st place is 1st, 2nd place is 2nd, etc. So again, on 36, it's going to be a permutation P, because order matters. The order in which they cross the finish line is literally the only thing that matters. And there are 7 boats to choose from, and we're assuming you're going to count from 1st to 7th here, so there's going to be 7 places to fill. Right, so P of 7, 7 tells us all the different finishes you can have for all 7 boats, all the different ways they can finish from 1st to 7th. 39, 10 magazines are competing for 3 identical awards for excellence in journalism. No magazine can receive more than 1 award. So there are 10 magazines, and they're competing for 3 identical awards. Does order matter or does it not? Well, I don't think order matters at all here because since they're the same awards, you're automatically those 3, whatever 3 you choose from, because there's 3 awards, they're all going to get the same thing, and the order that you choose them isn't going to matter again because you're getting the same thing. So order is not going to matter. It's going to be a combination. There are 10 magazines to choose from, and you are choosing 3 of them for these awards. So combination of 10 and 3 will give you all the different ways you can choose 3 magazines to give them, out of the 10, to give them the same award. 40 goes nicely with this because it says same exercise, but now assume all the awards are different. So let's just assume, for example, they're choosing 3 magazines, but they're going to give them the 1st, 2nd, and 3rd award. So in this case, the order is going to matter because choosing 3 to win is great, but if you shuffle those 3 in a different order, well, one person's going to get first and the other person's going to get third. And obviously that's going to matter to them, right? Whether they got first place, second place, or third place. So as soon as you make the awards different, in this case they didn't even say first, second, and third, but they could be, best sports article or best, whatever article. As long as they're different, if you shuffle them around, they're now getting different rewards, and that means they're getting different outcomes. So just changing the awards means it's going to be a permutation, because now there are different outcomes. Order matters. There's still going to be 10 to choose from, and you're still going to assign 3 of them, but because the order matters, it's going to be a permutation rather than a combination. Alright, so again, this is subtle, and when I first learned this, I don't think I learned it at all, actually. It was really confusing to me, and the way I kind of got through it was by thinking about slots here, right? So take these 2 examples, 39 and 40, think about if order matters. In 40, you're saying, okay, magazine A, B, and C, A is getting first, B is getting second, C is getting third. Now if you take those same 3 slots, first, second, and third, and you reorganize, you're still picking A, B, and C, so those magazines are still winning, but this time you're going to call it C, A, and B. Well, obviously this is a different order now, right? Because here, magazine C was getting third place, here magazine C is now getting first place. So that makes all the difference. Keep in mind though, if you ignore these numbers down here, like in part 39, when they all got the same reward, the same award, A, B, and C was the same thing as C, A, and B because they had identical awards. Didn't matter that the order you picked them if they're getting the same award. Right? So if you are in doubt about order mattering, make up letters or whatever magazines and switch them around in order and ask yourself, is this a different outcome? In 39, it is not a different outcome because still all 3 are winning. In 40, it is a different outcome because even though all 3 are still winning, they're winning in different ways. So these permutations and combinations, obviously you can use the formula to calculate it by hand, but we've been doing lots of stuff on the calculator, so let's continue to do that. Let me show you how you can do this on the calculator. So you're going to go to the button on the calculator that says Math, and if you go to that, if you look at the top, there should be several options, number, NUM, I think complex, CMPLX, and then the fourth one to the right is probability. It actually should be PROB, sorry. Depending on your calculator, I think it's different sometimes. So something like PRB or PROB for probability. If you use your arrow key and go over to that, your second option should be NPR. So that is for a permutation. The third option, by the way, is NCR, which will be for combination. So we're going to start by calculating the P of 10, 3 thing, the permutation of 10 and 3 on the calculator. So for that one, you're going to want to go to number 2 for NPR. Now, the problem with this is, depending on what model of calculator, but this will work for all models, I think. The way this is set up in PR is you have to enter your N first, then you select the NPR function, and then you enter your R. So if you want to do P of 10, 3, the very first thing you have to do is enter 10. So if you're still at your menu, by the way, for the NPR, you can always get out of any menu on the calculator by pressing second in the top left, and then the button right next to it is mode, and if you look above it says quit. So second quit will get you back to the home screen. So go ahead and get to the home screen, second quit, and the very first thing you have to enter is 10. So enter the number 10. Now go to Math, go to Probability, and choose NPR. Right, so you go down to number 2, NPR, and if you hit enter on that, you should have 10 NPR, and now you just need to enter 3 for your 3, and now you have 10 NPR 3. You can press enter, and you should get the number 720. Right, so it's a little cumbersome, but you literally have to enter it in this order. You enter your N first, then you choose NPR or NCR, and then choose 3 or enter 3, and then press enter one more time, and that'll calculate P of 10, 3. So similarly, if you want to calculate C of 10, 3, you have to start by entering 10, then go to Math, PRB, go to option 3 this time for NCR, press enter, and then enter your R, which is 3, and then one more time press enter on this, and you should get 120. Right, so the calculator will do all these calculations for you. Just keep in mind you could do these by hand relatively easily by following the formula and using the factorials. Alright, so we'll do 2 more problems here, a little bit more tricky ones. We're going to use some combinations and permutations. This one says the students in a 12-member advanced communications design class are submitting a project to a competition. Excuse me. They must select a 4-member team to attend the competition. So already we know there's 12 of them, and we're selecting 4. but this team has some conditions here. The team must have a team leader and a main presenter. So two of the positions on this 4-member team have specific roles, and it says the other 2 members have no particularly defined roles. And how many ways can this team be formed? Well, we're going to start with that team must have a team leader and a main presenter. So out of the 12 people, we're picking 2 people to fill specific roles. And remember, specific roles, in this case, they're going to mean that the order matters for that. So for that piece specifically, we're going to have a permutation because the order matters. We have 12 to choose from, and we are choosing 2. Right? So out of the 12 people, we are choosing 2 to serve on specific roles. That's why it's P, right? Because order matters for the team leader and the main presenter. Now, for the other people, we've already chosen our 2 here, so notice that means there's going to be 10 left to choose from. And it says the other 2 members have no particularly defined roles. Well, that's a pretty obvious way of them saying that the order doesn't matter in this case. Right? So for the other 2 people, it's going to be a combination. There's 10 to choose from because we already picked 2, right, for our leader and main presenter. And we're filling 2 slots, the remaining 2 team members, and they don't have defined roles, which is why they're combinations. Right, so the first part, permutation, because the order matters for our team leader and main presenter. We have all 12 to pick from, and we're picking 2 for that team leader and main presenter. Now, we've already picked 2, so we have 10 left to choose from. We're doing combinations this time because they have no particularly defined roles. That means the order doesn't matter. So we're doing combinations, 10 left, and we have to choose 2 more. Right? And we're multiplying these together by the fundamental counting principle. The number of ways we can choose our team leader and main presenter, the number of ways we can choose our other 2 team members. Multiply this all together, and if you crunch these numbers in the calculator, you should get 5,940. So there's that many different ways we can choose this committee, right? Out of the 12 members, we have to choose two people for the team leader and main presenter, and the two members for no particularly defined roles. There's 5,940 different ways we could choose this committee. That's what we just picked out here. Very similar problem here on page 633 as well, number 65. We have an academic computing committee at some college, and the committee consists of 5 administrators, 7 faculty, and 4 students. Okay, so that's what we have on the committee. Now we're going to form a 5-person subcommittee. So really quick, we had 5, 7, and 4. That's 12 and 4, 16, right? So that means there's 16 people total, and we're going to choose a 5-person subcommittee. So just keep that in mind. Now, on this 5-person subcommittee, the chair and vice chair must be administrators. Well, let's start with that. We know that there are 5 administrators to choose from, and we're going to put them in either a chair and vice chair position. So those are very defined positions. That means the order is going to matter. So we're going to do a permutation. We are choosing from the administrators, so there's only 5 administrators to choose from. And we're going to put them in 2 defined roles, the chair and vice chair. Right? So that takes care of our chair and vice chair. It says the remainder of the committee will consist of faculty and students. Right? It doesn't say any other specific roles here. There's 3 other people to go on this committee, right? Because it's a 5-person. So the remaining 3 people can be anyone from the faculty and students. Well, there are 7 faculty and 4 students. That's 11 people in total. And the order is not going to matter. So we're going to do a combination. 7 faculty and 4 students. That's 11 to choose from. 11 people out of the faculty and students. And we have to choose 3 remaining committee members because they said they wanted a 5-person subcommittee. Right? And we are going to multiply this all together just like last time. So let me go back through this one more time. Now first it says the chair and vice chair must be administrators. It's permutation because we're choosing a chair and a vice chair. And if you switch the order, that's going to matter. Order matters, so it's permutation. We're choosing from administrators, and it tells us that there's 5 administrators, so we have 5 to choose from. And we're choosing 2 because we have a chair and vice chair. There's just 2 slots. So this is that first part, chair and vice chair from the administrators. The remainder of the committee can be faculty and students. Well, there are 7 faculty and 4 students to choose from, so there's definitely 11 to choose from. And it says the remainder of the committee, well, we know there's going to be a 5-person subcommittee. We already chose a chair and vice chair over here, so that means there's 3 to choose from. and it's combination because the order doesn't matter. It just says the remainder of the committee. So we're assuming they don't have any particularly defined roles. So any of the 11 faculty and students, we're choosing 3 of them. That's why it's combination. And if you crunch these numbers and multiply them together, you should get 3,300 different ways you can fill this subcommittee. So there you go. It's pretty easy if you can get down the combination and permutation thing, and that all comes down to order mattering. And like I said, if you ever get stuck on that, try to make some slots, rearrange the slots, and ask yourself, is this a different outcome? So I hope this helps out. Let me know if you have any questions, and keep up the good work.